Welcome to the 16th lecture. From chapter 8 we are studying optimizing number of stages, and we in lecture 8:14, 2 lectures before, we studied that the chain delay is n times f times 1 over n, where n is the number of stages, number of gates in the stage, and number of gates in the chain. F is the path delay. The idea is that we introduce inverters that have g is equal to 1, and we know that the inverter whose m is 1 and it is a symmetric inverter, the g is 1, so the capital G remains the same, and the capital H is the ratio between this capacitor and this input capacitor C, so it also remains the same. This means F remains the same. So adding number of unit inverters just increases this n, where F remains the same. So we see a behavior in D like this, that it first decreases and then increases. So the value of n for which this is minimum, we call it optimum n. In lecture 14 we obtained the value of n optimum using hit and trial methods. We tried different values of n and we put those values in this expression and find the minimum value of D. Today we will do the same thing using an analytical approach. We know that in order to find the minimum point for this expression, we should differentiate it with respect to this and should put equal to 0. But before we do this, we'll do a small substitution, and that is that we'll assume another variable m which is equal to 1 over n. So this expression D becomes 1 over m f times m. Right, now we are going to differentiate this with respect to m. Partial over partial m, 1 over m f to the m. We know from the product rule that we'll first differentiate this first variable 1 over minus 1 over m squared, and the second will be written as such, and then we'll write first as such and we'll differentiate this second one. We know from elementary classes that this d by dx of a to the x is a to the x times log of a. We studied this in FSC and mathematics, in FSC and matriculation. In our elementary classes we derived this expression many a times. So we'll write it f to the m log of f, and this should be put equal to 0. Finally, we'll take this f to the m common. This is minus 1 over m squared plus 1 over m log of f is equal to 0. This f to the m divided by 0 on the other side becomes 0. Right, we can also take 1 over m common from the left hand side, and dividing that by 0 becomes 0. So 1 over m taken on the other side is equal to log of f. Since m was assumed equal to 1 over n, this means n is 1 over m. So 1 over m is n. So n optimum is log of f. This is how we can find the value of n optimum analytically. In our last example that we solved in 14th lecture, f was given to be 200. Initially n is 3, and we computed using hit and trial that n optimum is equal to 5. Now we can do it analytically. N optimum can be computed analytically by computing log of f, which is log of 200. Log of 200 comes out to be approximately 5.29, which we can assume it equal to be 5. We'll continue studying gate delays in our upcoming lectures. Thank you.